Good day, I'm Norman Wildberger. Today we want to have a look at the role of the term nothing, the concept of nothing in mathematics, which historically has been very interesting. It's a kind of nebulous concept, of course, that a lot of people have had different points of view towards. And what I'd like to do is I'd like to introduce a really dramatically new way, an additional new way of thinking about nothing and its role in mathematics. So in preparation for a discussion of that, let's have a look at some of the history. So a good place to go back to is the ancient Babylonians. Babylonians were sort of the geniuses of the ancient world long before the Greeks came on the scene. They had a very highly developed, original and powerful mathematics. So around 3000 BC, their culture developed in the Mesopotamian area, Tigris, Euphrates rivers. And they had a sexagesimal system, which means base 60. Very interesting. And they also used a floating point positional system, very much like the one we do. So they used basically only two symbols. There was a symbol for 1 and a symbol for 10, which they wrote with this sort of wedge-like implement that they used to write on clay tablets. So to express 47, they would make 4 of these 10s and 7 of these 1s, and they would arrange them in something like this, and that would be 47. So they used these to represent the numbers from 1 to 59. They are the corresponding digits for the Babylonians, just as the numbers 1 to 9 are for us. Well, actually, we use 0 as well. So then otherwise what they did is they had a base 60 representation so that they would clump their numbers in various places linearly. So this representation here, there'd be a 47 visible there, and here you can see a 21, and here there's some kind of space, and over here there's a 2. So this would represent for them, well, 47, 21 times 60, so this would be the 60s column, and 0 60 squareds, and 2 60 cubes. So altogether 2 times 60 cubed plus 21 times 60, we'll ignore this one, plus 47 for a total of what we would call 217,307. Now an interesting aspect of their arithmetic was that they didn't really have a very clear or concrete representation of the decimal point. So there was some kind of ambiguity in their system. On another occasion, they could have represented this as being 21 ones, 0 60s, 2 60 squareds, and 47 over 60. This gave them a flexibility that's actually quite useful. So what's interesting for us is their use of the space to represent zeros. They had this very clear idea they're going to work powers of 60, and if we're missing a power of 60, we'll just leave a space. We're not going to put anything there. The reader should be able to see that there's a space in here and sort of register that we're missing the 60 squareds. But we have 60s and 60 cubes. So this is going back quite a long time, and so this really is a use of the decimal kind of system, very much like the Hindu Arabic one that we use, with the notable exception that they're working in base 60 and that they don't have an explicit form for a placeholder, but they're using the space pretty well exactly in the corresponding way. So they can certainly deal with numbers pretty well the same way that we can. Now the Babylonian culture lasted a long time. We're talking about several thousand-year span. And in the later part of this time frame, around 300 BC, there was a great flowering of astronomy and work in that direction. And part of that story was a very interesting development, that the Babylonians started to use actually an explicit symbol to represent this placeholder that previously they just had a space for. So this is actually the first really recorded use of a symbol for 0, which predates the Hindu development actually. So here's what they did. They employed basically a similar kind of symbol to their number 2, just these two sort of wedges coming down. But they're now at an angle, and they're kind of a little bit above the regular reading of things. So they could see that as we're reading this here, this symbol here represents not a explicit number 2, but rather it's a placeholder for the 0. So they could read this as 2 times 60 squared plus 0 times 60 plus 24, which would be our 7,224. Now, this symbol here really is only being used as a placeholder. Okay? It's to make more explicit, more unambiguous the fact that there is nothing in this place particularly, right here. It's not the case that this symbol was used as a separate number. So that was the development that the Hindus get credit for. Okay. So they did not have this idea that there's a new number which is these two slanted symbols. Nevertheless, it's really the first use of the term 0, and the astronomers actually did employ this notation. However, it was never really equated with nothingness. We didn't have this idea that there's nothing and that nothing is actually represented by this particular symbol explicitly. Now, many histories of mathematics concentrate on the Mediterranean area and the Asian developments as well. Of course, there was also very important culture, in fact, cultures in the Americas, Mayans, Aztecs, Incas. And the Mayan culture is particularly interesting because they have a very interesting arithmetic and quite a sophisticated calendar reckoning and corresponding astronomy. So in Central America, the Mayan culture, well, it was been around from at least 2000 BC, but there was a classic period from 250 AD to 900 AD that things really developed in a rather sophisticated way. And we know that they had a so-called vigesimal system, which is base 20. And it was actually relatively efficiently written down with only 3 symbols, more or less. A symbol for 0, which was this sort of odd kind of eye-shaped thing. And in fact, there were quite a lot of variants on the way of writing that 0. And then there was a dot, which represented 1, and a horizontal bar, which represented 5. So they would count 0, 1, 2, 3, 4, 5 like this, 6 like this, up to 19. And then after 19, well, then they had a base 20 system. So these were sort of the basic digits that they would use. And then they would have these things stacked up in a vertical system, not a horizontal one. And they were very interested in astronomy and calendars. And that explains a little bit that their system for stacking things up was not quite what you would expect in a base 20 system. There was an important twist involved. So here, for example, is a Mayan number. So we see these symbols stacked one on top of each other. We recognize this one here is the symbol for 11 because it has 2 5s and a 1. And then there's a 0, and then there's a 2, and then there's a 3. So what did these various things represent? Well, the bottom one was 11, or 11 ones. And here we have 0 20s. But the next level does not correspond, as we might imagine, to 20 squareds. This next level actually represents how many 360s we have. So this would mean that there are 2 times 360. And the next level represented 20 times 360. So after this, we keep multiplying by 20, but we have this basic 360. So this means that we have 3 20 times 360s. So I think that's a total of 22,361. So there's certainly an unevenness to these levels. We have 1s, and then 20s, and then 360s, and then 20 times 360s, 20 squared times 360s, and so on. And the reason for that is because they were very interested in the calendar. They had a very good understanding of astronomy and the year especially. So they knew there were 365 days in a year, and so 360 was kind of the closest to that. So they had a splitting up of the 360 into 18 periods of 20. So it was 18 times 20, and then there were 5 left over. And it was because of that 360 that appeared in their calendar that they had a number system that kind of reflected that aspect of things. So their numbering, or their numerology, I think was very closely connected somehow with the year and days and time. So as an idea of their accuracy, they knew that the solar year actually was a little bit more than 365 days, and effectively they knew that in our language that there were 365.242 days in a year, while our current understanding is that it's 365.242198. So this is pretty impressive kind of accuracy in their understanding. So the Mayans did have a symbol for 0, and they used that in their positional representation of numbers, not so much different from the Babylonians. Now, what about the ancient Greeks, who were, of course, sort of the powerhouse of ancient mathematics in terms of developing the geometry and mathematics that we know today? Well, their arithmetic was not as impressive as their geometry. They certainly knew a lot of interesting things about arithmetic, but their actual notational arithmetical tools that they had were not always very powerful. In fact, often they would use the Babylonian system to make calculations. They had a kind of an alphabet kind of system where they represented numbers by letters of the alphabet. But this was cumbersome, and they did find that the Babylonian system was useful to borrow. But we can also see that they philosophically were not inclined to think about 0 as a very important concept. Philosophically, they did not like, or they were mistrustful of this idea of the void or nothing. And maybe we can attribute that a little bit to their emphasis on geometry. So for example, if you have a very geometrical approach to numbers, which they did, they like to think about numbers as being represented by physical or geometrical patterns or designs. So for example, triangular numbers figured prominently in their thinking, 1, 3, 6, 10, and so on. And if you're thinking about something like triangular numbers represented in this very physical way with these little triangular piles of circles, then it's not very natural for you to want to consider 0. 0 doesn't really figure in this, because it's clear that this pattern of triangular numbers really ought to start with 1. That's the starting point. And that's the next one, and that's the next one. It's somehow unnatural to talk about 0 in this context. So, aside from their geometrical inclination, they also had very strong ideas about philosophy. They thought very deeply about what the world was really about. And they came to this conclusion that it was not really proper to try to make something out of nothing. Right? So, the idea of nothing or a void was not sufficiently rich to be able to convert that into something. In some sense, that's what we're doing, right? When we're thinking about 0, we're thinking about nothing, and then we're writing a symbol to represent that nothing, and then that symbol becomes something that we manipulate along with other numbers. So in some way, we're creating something out of nothing by the use of a modern symbol like this. But the Greeks did not like that way of thinking. They thought of both of the infinity and the void as things to be avoided conceptually. They were problematic. So this philosophical orientation was well expressed by a prominent Greek philosopher, Parmenides, who was a big influence on Plato. And he wrote on this topic in a number of different places. So here are some quotes from Parmenides. He says that it is necessary to speak and to think about what is, for being is, but nothing is not. Okay, this is in the direction of we should talk about things which actually are. We can't talk about things which are not because they're not. Another quote, nothing comes from nothing. This idea that you can't take nothing, that concept nothing, and create something out of it. That's a vacuous kind of activity, and you shouldn't do that. So we also read from him that for this view that which is not exists can never predominate. He's saying that the idea that we can consider that which is not, so that which is not, and actually objectify that and create something out of it, that's not a valid way of thinking. So Parmenides had a big influence on Plato, who actually named one of his dialogues after him. And this really, was representative of the Greek way of thinking and explains to some extent why theirs was not a fertile arithmetic for this idea of a symbol for zero to develop and blossom. I'd like to mention also that the Hebrew tradition is also in this direction. So in the Hebrew tradition, the void is also treated with suspicion, and one tries to avoid it. So the void is considered to be a state of separation from God. So first there was the void, and then there was God creating other stuff. And so the void is some kind of thing that we want to stay away from. It's not pleasant. So there's philosophical orientations that are very close to people's thinking about this subject. What does it mean to contemplate nothing? For example, what would the world be like if there was nothing? It's a very profound question. And people have been thinking about these kinds of things for a long time. And one's orientation towards this kind of philosophical position would naturally influence one's mathematics and the kind of mathematics that one might want to do. And so now we come to the heroes of this story, the culture that really introduced zero the way we know it now. And now we recognize that this was a fundamentally, crucially important development in the history of science. And I have talked about that in a previous video on the Hindu-Arabic numbers. So we're talking about ancient Indian philosophy, religion, mathematics. The Indus Valley culture goes back to around 3000 BC. But we have evidence to suggest that they were thinking along somewhat modern lines around 350 BC, where the Brahmi notation for numerals was starting to look pretty similar to the modern system. And they had a positional base 10 system that was in place around 500 AD. So here are some original kind of numerals. You can sort of see some similarities with some of our current numbers. Now, what's interesting in the Indian point of view here is, amongst other things, is that their philosophical orientation seemed to predispose them towards being happy with the idea of thinking about nothing as a legitimate object for study and incorporating into mathematics. The Indians were not afraid of nothing philosophically. In fact, they had a kind of a reverence for it. They were very comfortable with the idea of nothingness and emptiness. Maybe simplistically, we could say that nothing was viewed as a state from which we arise, and it's a state that we eventually return to. So maybe from an Indian point of view, there's nothing to be afraid of there. It's a sort of natural part of the whole story. In any case, in Sanskrit, they had lots of different words representing different aspects of emptiness, void, nothing, and so on. So they conceptually had a framework in which nothing naturally played a reasonable role. And this was then, of course, very crucial in this development after they have these numbers to eventually introduce actually a symbol for zero. That turned out to be another number essentially on par with the ones that they already have. So we have evidence that dot for zero was in place around 200 BC. And that gradually was then replaced with the more familiar round circle zero. And by around 500 AD, it was in place as a placeholder in a decimal system pretty well the same as we have today. And then we come to Brahma Gupta, prominent Indian mathematician and astronomer, who around 620 AD took an important additional step to establish 0 not just as a placeholder in a notational system for more general numbers, but actually to recognize that 0 was an entity that had an independence, it had a role to play, and that role in fact turned out to be a rather important one in arithmetic, so that 0 could be the result of an arithmetical computation. So 5 minus 5 equals 0. That is then an equation that you could actually write down, whereas formerly it was difficult to say that. 3 plus 0 equals 3. You can multiply by 0. 0 times 7 equals 0. You can subtract 0 from something. 4 minus 0 is 4. In fact, he even discusses division by 0 and had an understanding that if you take a number and you divide by 0, you're getting something like infinity. All right, so this is a very huge step, and I've talked about the importance of the Hindu-Arabic system in many places, and it's really not possible to overestimate the importance of this whole development in the modern world, the world that we live in, the highly technological, mathematical world, rests very solidly on this. Well, to us it seems relatively simple and straightforward because we've been taught from a very early age over and over and over again how this numerical system works. But it's actually full of subtlety and richness, this Hindu-Arabic system. And the 0, of course, plays a very important role. Now, if we move ahead to European times, to more modern times, the role of nothing, or 0, was still actually quite contentious in the 16th, 17th, 18th centuries, where people were examining the physical universe much more carefully, and for example, questions about whether it was possible to consider empty space or not were being discussed. So the ancient Greeks had reservations about being able to treat empty space as something sort of independent of other stuff, but 17th, 18th century scientists started investigating the possibility of thinking about space as being free from any stuff inside it, trying to create a vacuum, for example. And in the framework of Newton's laws, I mean, these are sort of operating in sort of empty space quite happily. But if we forward then again to 20th century physics, things become then again more complicated. And the confidence and the certainty that maybe 19th century mathematicians had about the void or vacuum started going the other direction again, and people started becoming more aware that this was still a rather problematic concept and actually full of subtlety. So modern 20th century physics treats the vacuum as a really central but very complicated and rich kind of concept. So to the modern physicist, the vacuum is full of possibilities. It's not at all just empty space and nothing in it. So this is largely due to the role of quantum mechanics and a certain principle called the uncertainty principle, which roughly tells us that we can't really know everything about a situation, let's say. Right? And that goes for any kind of situation, even a situation where it looks like there might be nothing in it. So if you have a situation where you have some empty piece of space and there's nothing in it, you still can't know everything about it. And that can be interpreted as saying that there's a lowest possible energy sort of for empty space, but you can't really make that energy completely zero. There's always some energy there that's a kind of a bottom possible energy, but that supports various strange things that might happen. So in the modern vacuum, physicists think that there's all these simultaneous creation and annihilations of particle and antiparticle pairs that are sort of instantaneously happening, where we have a little bit of empty space and suddenly there's an electron and a positron. So an electron has an anti-particle called a positron, and these things can be created sort of out of nothing, more or less, and then shortly thereafter they can then annihilate each other and go back to nothing. So that this quantum vacuum is sort of seething with all these possibilities of these particles emerging for a short period of time and so on. So it's very rich and mysterious kind of concept. So the modern physicist now is returning to not being so sure what nothing means, actually, in the kind of physical kind of world. And so there's a very interesting story about nothing, and I think the last word has not been said. And I would like to really emphasize the possibility that maybe even in mathematics, which, I mean, is at least potentially independent of these quantum mysteries, even in mathematics, there's the potential room for thinking about nothing, or the void, in a different or an additional way to what we already have. So I don't necessarily want to change the role of zero, which is great, you know, a very important concept in our number system and so on. But I do want us to think more liberally about the possible role of nothing, a more fundamental kind of nothing than actually zero. So zero is still something that's been created out of nothing. But I want to propose that there's room in mathematics for nothing, which is still just nothing. Okay, it hasn't been converted into something. We don't have to create something from nothing. We can think about nothing itself. And that can be a concept that can help us. And so, okay, that's what I want to do. I want to introduce nothing into mathematics again, but in a more primitive, fundamental, really void kind of fashion. I think there's a role to play, and that's especially clear when we have this multi-set point of view that we're getting used to here. So in our next video, I want to talk about nothing in a multi-set context and why mathematics really does need new thinking about nothing. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.